In this video, we're going to look at 5.4, the properties of definite integrals. And in this first slide, we're looking at converting from Riemann sum notation to the definite integral. This general form that's shown here is more specific than the examples down below. In the examples down below, the a value is always 0. Okay, so taking a look at this first example, we know that the width of our rectangle that we're adding up is based on the change in x divided by the number of partitions. Okay, and so we can always look at this piece, 3 over n, as indicating what is our difference between b minus a. So our change in x is 3, and we are starting at 0 for our limits of integration. We need to look at this term here as the height of the rectangle. So here we're talking about the width of the rectangle, here we're talking about the height of the rectangle, and if we add up all those areas, we will get the area under the curve. So this term is going to give us a picture of what our function is. So we're looking at x squared as our function. Okay, let's take a look at question B. So again, this term, 2 over n, is indicating our width, this term indicating our height, and our height has to come from our function. Here we have a cubic function, so we're looking at the integral from 0 to 2 of x cubed dx. Example C, our change in x is pi units. That means our limits of integration go from 0 to pi. Our function, indicated by this height, is the sine function. So we're finding the area under the curve, under the sine curve, between 0 and pi. In example D, again, we have a change in x of 2. So our limits of integration go from 0 to 2. Our function looks to be a quadratic function of the form 1 plus x squared dx. Okay, in this last one, it looks a lot like D. What is different about it is that this term is a 4i instead of a 2i as the last one. So I'm going to speculate that this was 2 times 2i over n as that term. So this definite integral will be 0 to 2 of 1 plus 2x plus x squared dx. Okay, if we had another example where we had the limit as n goes to infinity of the summation of all these rectangles, and it looked like 5 plus 3, 7 plus 2i over n squared. That's supposed to be an n. Okay, then this looks more like the general, and this 7 is indicating where we're starting. So our change in x is still 2 units, but we are starting at 7. So this integral starts at 7 and goes to 9, and our function would be 5 plus 3x squared dx. Okay, doesn't look like you're going to see anything that complicated. They're going to keep it pretty simple. Okay, we're going to look at the properties of integration geometrically. So just what they mean. So we have, I'm going to take a look actually at this one first and this one second, because we've kind of looked at these already. And so this question says, what is the integral from a to b of c times dx, where c is any constant? So here's a graphical image of the function y equals c, and if we are going to find the area under the curve on the interval from a to b, we are just looking at the rectangle b minus a as the base times the height of c. So we could call this c times b minus a, or b minus a times c. Okay, in the second example, it says find the integral from a to b of f of x. And this is let me actually shade the areas. This is what we've been looking at in terms of finding the area under the curve. Now we know if we can antiderive this function, and capital F is the antiderivative, we will get f of b minus f of a, according to the total change theorem. Okay, so now I'm going to come back to this first one here. I'm going to call it example 3 though. And the limits of integration say we're going to go from a to a. In other words, there is no horizontal change, okay, as in this b minus a. And so the integral from a to a of f of x dx would be 0. There is no area. Okay, what happens if we look at the integral from b to a? So we're not going forward from a to b, we're going backwards from b to a. Okay, well remember, here it was b minus a times some f of, I'm going to call them x of I, heights, right? All of these heights, so that we're going to get areas of rectangles that we'd be adding up. How does that compare to this if we do a minus b? Okay, these two are only different by a negative sign. Okay, and so what happens is the integral from b to a of f of x dx is the same as the negative integral from a to b of f of x dx. Okay, moving on, we have got a few more geometrical, looking at the integration geometrically. Okay, so the blue function here, and I'm going to call this number 5, is my f of x function. The integral asks for the integral from a to b of a constant k times f of x. So as an example, if k were 2, this would cause a vertical stretch in my function, making it twice as tall. I've tried to illustrate it being twice as tall. Okay, and so we're looking at the area under the curve of the purple curve, in this case 2f of x, right? And so what is happening is, well, if the heights are twice as tall, then the area is going to have an extra factor of 2 in it. Now another way to look at this is we could say, we could pull that coefficient out and say, okay, we're going to find the area under the curve of f of x. but we are going to double it. Okay? All right, so it's a little bit tough to tell with this example. Perhaps if you thought about a straight line curve, like a constant, if this was y equals 3, and then you double to get y equals 6, and you're looking on the interval from a to b, then it clearly makes sense that the area has been doubled. Okay? So any coefficient times a function can be pulled out as a coefficient times the integral of that function. All right, number 6. Number 6 is looking at the integral from a to b of the sum of two functions. So I'm definitely going to find the area under the curve between a and b on f of x. But I am also going to find the area under the curve from a to b on g of x. And we're going to add those two together. Now, if you actually think about adding the two functions together to start with, then the new function, f of x plus g of x, is going to be, in this example, have higher y values than the current y values. Okay? So in effect, you're adding the two areas together, the area under each curve together. Okay, example number 7. We have the integral from a to b of f of x dx. And this time, we're given some information that C is a point on the interval from a to b. Okay, so what we're looking at is breaking up the interval, and we could describe the sum of two integrals, the integral from a to c of f of x dx, plus the integral from c to b of f of x dx, as equivalent to the integral from a to b. So those are properties of definite integrals. They're listed here in the notes, and they might come in handy if we're working with finding integrals in the future. And it's good to know the notation, so be careful of the switch in the limits of integration. We have the integral of a sum. This could be also of a difference. Okay. All right, we're going to stop this video and I'll bring up some examples in the next video.